Okay, now we're going to look at something that we've kind of introduced before when we started looking at RC and RL circuits. We're going to look at them in terms of AC signals and frequencies. And what we're specifically looking at is filters. So chapter 20 is filters. Filters are actually just tuned circuits. We're going to start to see the effects of what capacitors and inductors do in a circuit when you start applying the operating frequency or running the signal, the operating frequencies through at various frequencies. And so the idea behind these types of filters or circuits is to look at how they respond, how the output responds. Some of you are probably very familiar with amplifiers, stereo amplifiers. And you have your high end, your tweeters, you have your low end, your bass, and you have your mid-range. And the frequency response of the amplifier is based upon tuning the circuits, the tuned circuits that send part of the signal one way, part of the signal the other way, and let some of it be. All of the high frequency response go to the tweeters. All of the low frequency response goes to the bass. And then the mid-range just stays put. So we're going to take a look at fundamentally how that works. So in low pass and high pass filters, we're going to look at how the capacitors, in this case, starts to adjust or react to a frequency. So the circuit output voltage then, in this case, in this schematic that we see here, is developed, in fact, across the capacitor. And we've seen how capacitors are frequency dependent. Resistors are not frequency dependent. So what happens is, as the frequency changes, that capacitor is going to start reacting differently. And how does it do it? Well, it does it by acting like a resistor and changing the amount of resistance, the reactance, through that capacitor. So we have the output voltage varying then as the capacitor voltage varies. What happens to the resistor and the capacitor as the frequency varies? Well, X sub C is the greatest in this case at low frequency. So the capacitive reactance, which is the ohmic value, is greatest at low frequencies. Therefore, V sub C then will be the greatest at low frequencies. So at low frequencies, it starts choking the current flow through that capacitor. If we plotted a graph then of the output of the voltage versus the frequency, we would see at very low frequencies V out equals Vn. Okay, so if we look at the little curve here, we can see something happens here as V out then starts to change as the frequency starts to change. We start to see what's called a little cutoff or a break or a corner frequency here, where the frequency response starts to take a nosedive. And that nosedive is based on how much the output voltage is changing with the change in the frequency. As the frequency increases, then the capacitive reactance, X sub C, then decreases, and so does the output voltage. As the frequency increases, then at some point, we have the capacitive reactance equal to the resistance. And this occurs right there where that dotted line is, the cutoff frequency. So because X sub C is equal to the resistance, that cutoff frequency, we have other conditions that also exist. The first one is the phase angle. The phase angle typically is at 45 degrees, minus 45 degrees in this case. The voltage drop across the capacitor will match that of the resistor, and it happens to be 0.707 of the input voltage. So what you're seeing here is 70.7% of the input voltage occurs when V sub C and V sub R are the same. The current, again, follows that same rule. 0.707 times the max current occurs. And then we have something called the half power point, or the point where the power is equal to exactly 1/2 of the max power. Later we're going to see something called the 3 dB point as well. So we'll start seeing different terms and applications as we move along. So let's take a look at an example here. Sometimes it's the easiest to understand if we apply an example. They tell us, again, to look at the same circuit here. It's our RC circuit. We're going to let the input voltage equal 10 volts. The resistor is a 10 k ohm resistor. The capacitor is a 10 nanofarad capacitor. From that information, then, can we calculate the cutoff frequency, the output voltage, the voltage drop across the resistor, current, power, the phase angle, and all of this at the cutoff frequency? So they've given us here a rectangular representation then of the circuit. The impedance then for this circuit, R minus J X sub C, is equal to 10 k ohms minus J 10 k ohms, which gives us then, if we convert those to that to a magnitude, 14.1 k ohms at an angle of minus 45 degrees. So in this case, what we're looking at here is those two values, again, where we said X sub C equals R. So the current itself then will be calculated Vn by that magnitude of the impedance. 10 volts divided by 14.1 k ohms gives us, lo and behold, 0.707 of milliamps of the current then at that point. The output voltage then equals V sub C, which equals the current times X sub C, 7.07 volts. So you should start seeing a theme as we're moving through these values. V out then is equal to the input times the sine of theta. So the input 10 volts times the sine of minus 45, 7.707. The resistor, I times R, again, 7.07. Okay, we could also calculate it. Okay, no, they're just showing us the value. Okay, so we did it by Ohm's law, we did it by trigonometric functions. And then the power itself, 0.707 milliamps times 0.707, and we have 5 milliwatts of power. Our angle was given then that we solved for, that was given to us above, a negative 45. And then using the values given, we can calculate the cutoff frequency. The cutoff frequency is defined by 1 divided by 2 pi RC. So in this case, 10 k ohms times 10 nanofarads times 2 pi divided into 1 gives us an operating frequency, or a cutoff frequency, at 1.59. And again, that's that point right there where we start to get our corner or our cutoff. So if we reverse the position of the components, we now have a high-pass filter. The previous example was a low-pass filter. So you can see in this case, now we've reversed the position. The output is taken, in this case, across the resistor instead of the capacitor. Now the output set up this way causes VO then to increase, the output frequency to increase with frequency. The cutoff frequency remains the same. So if we look at another example, the input voltage, 5 volts, 4.7 k ohm resistor, and a 100 nanofarad capacitor. Find the cutoff frequency, V sub output, the power, all at the cutoff. So again, if at our value here of calculated for the cutoff frequency is equal to that representation, and when we insert our resistor and our capacitor values, we get 339 hertz is the cutoff. Again, that's where the knee starts to occur. Using our value here for the impedance, R minus J x sub c. Again, since we're dealing with the point where x sub c and R are the same, R was given to us as 4.7 k ohms, and x sub c then becomes 4.7 k ohms, which gives us a polar value of 6.65 at an angle of minus 45 degrees. Okay, 6.65 k ohms. Calculating the current, V sub n divided by the total impedance, gives us 742 microamps. V out then is equal to Vn times the sine of theta, which gives us 3.54 volts, and the power I times V out 2.66 milliamps. Okay, so you notice now our output looks a little different here from the original one. On the original one, notice how the curve drops off for a low-pass filter, and on the high-pass filter, it increases. So the curve of the output voltage versus frequency for a high-pass filter that we just covered. Okay, so when we come back, we're going to revisit something that we talked about earlier, Norton's and Thevenin's theorems. These two theorems help us to simplify circuits so that we can do our analysis more simply.